There is a place in the highlands of Peru where the air is thin and the light arrives differently than it does anywhere else on Earth. At nearly 12,000 feet above sea level, the sky above Cusco carries a sharpness that makes colours look almost unreal. The terracotta rooftops, the pale colonial walls, the dark green of distant hills pressing against a blue so deep it feels like a different atmosphere entirely. Most visitors arrive here and immediately feel the altitude in their lungs, a quiet pressure that reminds the body it is somewhere it was not designed to be. But there is something else here that presses on the mind in a different way. On the northern edge of the city, where the cobblestone roads give way to rough terrain and the tourist crowds begin to thin, there is a structure that has stood for longer than anyone can say with certainty. Its name is Sacsayhuaman. Locals pronounce it closer to sexy woman, a joke that foreign visitors hear on every tour. But the moment you stand before it, the laughter fades. What replaces it is something quieter, something that sits at the back of the mind and refuses to leave. The walls of Sacsayhuaman are built from stones so large that the biggest blocks weigh over 100 tons. Some researchers estimate certain foundation stones approach 200 tons. These are not the neat, rectangular blocks you might picture when you imagine ancient construction. They are irregular, massive, each one shaped differently from its neighbour, with multiple faces and curved surfaces, fitting together in a pattern that looks almost organic, like the cells of some enormous living thing, pressed together and then frozen in place. There is no mortar between them, not a drop, not a trace, yet a sheet of paper cannot be slid between most of the joints. In some places, the gap between adjacent stones is measured in fractions of a millimetre, tighter than many modern construction tolerances, achieved without the instruments, the software, or the machinery that modern construction depends on. And here is the thing that geologists and engineers keep returning to. The thing that keeps this question alive in serious academic circles, despite the tendency of institutions to dismiss it. The stones don't just fit together. They appear to conform to each other. The surfaces at the joints are not flat planes meeting flat planes. They are curved, irregular, three-dimensional interfaces. One stone surface matching the contours of its neighbour with an intimacy that suggests the two were shaped in contact, not shaped separately and then joined. In 1997, a team of engineers equipped with laser-guided cutting technology attempted to replicate a single joint from this wall. They had access to modern diamond-edged cutting tools, digital measuring instruments, and computer-aided design. They failed, not by a small margin, not close enough to say they almost had it. The gap between their replica joint and the original was measurable, consistent, and unambiguous. The technology of the late 20th century could not match the precision of a construction that, by conventional accounts, was assembled using stone hammers and human hands. That is not an alien mystery. That is not the premise of a conspiracy theory. It is a documented engineering result, arrived at by professionals applying the tools of their trade to a specific testable problem. And it is the question at the heart of everything that follows. This documentary is not going to tell you who built these walls. It is not going to propose a simple answer to a question that has frustrated serious researchers for generations. What it is going to do is follow the evidence, slowly, carefully, through geology, chemistry, history, and human memory, to the place where the known ends and the unknown begins. Because that boundary is closer than the textbooks suggest. And what waits just beyond it may change the way you understand what human beings are capable of. To understand why the walls of Sacsayhuaman confound modern engineers, you first have to understand what kind of stone they are made of, and what that stone's normal behaviour looks like. The primary material is andesite, a volcanic rock named after the Andes Mountains, where it is found in abundance. Andesite is not the hardest rock in the world, but it is far from soft. It sits comfortably in the middle range of geological hardness, resistant enough to have withstood earthquakes that levelled every colonial Spanish building constructed nearby, dense enough to require significant force to shape even with modern tools. Under normal conditions, andesite does not flow, it does not bend, it does not press itself into the contours of a neighbouring stone. When you cut andesite with a tool, whether a stone hammer, a metal blade, or a diamond-edged saw, the cut surface bears the signature of that cutting process. There are striations, linear marks, fracture patterns that follow the direction of applied force. The surface tells the story of how it was made, if you know how to read it. This is what geologists call surface texture analysis, and it is one of the most reliable ways to determine how a stone was worked. A surface shaped by abrasion looks different from a surface shaped by percussion, which looks different from a surface shaped by heat, which looks different from a surface shaped by chemical action. Each process leaves its own fingerprint in the crystalline structure of the rock. When geologists applied this analysis to the joint surfaces of the Sacsayhuaman walls, surfaces that had been hidden from view for centuries, protected by the tight fit of neighbouring stones, they found something that did not match any of those expected fingerprints. The surfaces at the joints showed what researchers began calling flow features, patterns in the microcrystalline structure of the stone that resemble the texture left behind when a material has moved, conformed, and then solidified, not cut, not abraded, not fractured, moved. This is the kind of description that requires precision, because the word flow carries implications that need to be handled carefully. Stone does not flow at room temperature under any natural process that operate on a human timescale. For stone to flow, to behave as though it were plastic or semi-liquid, it must be subjected to conditions that are, in the ordinary world, extraordinary. Temperatures in the hundreds or thousands of degrees, pressures found only deep in the Earth's crust, or chemical alterations that fundamentally change the mineral structure of the rock. And yet the flow features are there, described by geologist Dr. Jan Sammer, documented in the findings of multiple independent researchers who examined the Sacsayhuaman joint surfaces. These microscopic textures are consistent across different stones, different sections of the wall, and different research methodologies. The stone had never been near a volcano. The walls show no evidence of fire exposure. No thermal stress fractures radiate outward from the joints in the patterns you would expect if intense external heat had been applied. Whatever produced these flow features, it was not a conventional geological process, and it was not ordinary fire. The interlocking geometry deepens the puzzle further. Polygonal masonry, the term for this style of construction, where stones are shaped with multiple irregular faces, is found at ancient sites on multiple continents. But the Peruvian examples are exceptional in one specific way. The interlocking is not merely two-dimensional. When researchers probe the joints with thin instruments, or examine cross-sections in areas where stones have shifted slightly over the centuries, they find that the fitting continues inward. The stones do not just meet at their visible faces. They reach into each other, fitting in 3 dimensions simultaneously, creating a mechanical interlock that would be extraordinarily difficult to achieve by cutting 2 separate stones to matching tolerances, and essentially impossible if the cutting were done by hand, with stone tools working from the outside. The stone is speaking, in other words. And what it is speaking, quietly, in the language of crystal structure and microscopic surface texture, is that something happened here that we do not yet have an adequate explanation for. The mainstream explanation for the Sacsayhuaman walls, the one taught in universities, printed in archaeology textbooks, and repeated on museum plaques, is a story of organised labour. Thousands of workers, the explanation goes, quarried stone from sites several kilometres away, moved those stones using ramps, ropes, and log rollers, and shaped them using harder stone hammers and abrasion, fitting each block through a process of trial and error, raising a stone, checking the fit, lowering it again, grinding the surfaces against each other until they conformed. Repeat this for long enough, with enough workers, enough patience, and enough time, and you eventually arrive at the walls that stand today. This explanation is not ridiculous. It has genuine archaeological support. The quarry sites are real. The remains of ramps and earthworks have been found at some megalithic sites. Experimental archaeology projects have demonstrated that large stones can be moved across significant distances using only human muscle and simple, mechanical principles. The logistics of massive labour organisation are well within what we know the Inca and pre-Inca civilizations were capable of. But the explanation contains a gap, and the gap is in the shaping. Moving a stone and shaping a stone are 2 entirely different problems. The movement problem has been largely solved. We understand, in broad terms, how large stones could be transported. The shaping problem has not been solved. The trial and error grinding explanation accounts for two flat surfaces being brought into rough alignment. It does not account for three-dimensional interlocking at sub-millimeter tolerances across hundreds of individual stone interfaces, each one unique in its geometry. In 2011, an experimental archaeology team working in France spent 6 months attempting to construct a single course of polygonal masonry using only tools and methods available to pre-industrial cultures. The team was skilled, patient, and methodologically rigorous. At the end of 6 months, they had a wall. It was structurally sound. It demonstrated that the basic concept of polygonal masonry was achievable without modern tools. When they measured their joint tolerances against the Sacsayhuaman standard, the gap between the two was not subtle. The best joints their team produced were off by a factor of 40 compared to the precision found in the Peruvian originals. 40 times less precise? After 6 months of skilled work, using a team that knew exactly what they were trying to achieve. The mainstream explanation is not wrong about everything, but it is incomplete, specifically in the place where the mystery lives. And incomplete explanations have a way of holding open questions at bay without actually answering them, letting them accumulate quietly in the spaces between what we say we know and what the evidence actually shows. This is one of those quiet spaces. It has been accumulating for a long time, and the question inside it is growing harder to ignore. The Inca Empire, at its height in the 15th and early 16th centuries, was the largest empire in the pre-Columbian Americas. It stretched from the northern borders of what is now Ecuador through the full length of Peru, into Bolivia, and down through Chile and Argentina, a territory covering nearly 4,000 kilometers from north to south, bound together by an extraordinary network of roads, relay stations, and administrative centers. The Inca were sophisticated organizers, brilliant engineers by any reasonable standard, and accomplished builders in their own right. But here is the thing that most popular accounts of Andean history skip past without pause. The Inca did not build the most extraordinary stonework in their territory. They built on top of it. The distinction is visible to any careful observer at the major archaeological sites around Cusco, at Sacsayhuaman, at Ollantaytambo. At the base walls of temples throughout the Sacred Valley, there are two unmistakably different construction styles layered one above the other. The lower courses, the massive, irregularly shaped polygonal stones fitted together without mortar at impossible tolerances, belong to one tradition. The upper courses, neat rectangular ashlar blocks, well made but clearly distinct, belong to the Inca. The line between them is not always sharp, but it is always real. Archaeologists who study these sites can identify it immediately. The Inca built upward from a foundation they did not create. When Spanish conquistadors arrived in the early 16th century and began the work of understanding the civilization they were in the process of destroying, they asked the Inca about these walls. The question was natural. Who built this? The Inca were not humble people. They named their rulers, celebrated their conquests, and attributed their roads and temples to specific emperors whose reigns were recorded in their oral traditions. But when the question of the great polygonal walls arose, the massive lower courses that formed the foundations of their sacred spaces, the Inca gave answers that the Spanish chroniclers found puzzling and recorded faithfully. Pedro Cieza de Leon, one of the most careful and credible of the Spanish chroniclers, recorded an exchange with Inca elders about Sacsayhuaman that has stayed in the historical record for 5 centuries. When he pressed them for an explanation of who had built the lower walls, the elders fell quiet. Then one of them told him something that Cieza found impossible to categorize. It was built in a single night, by beings who knew things that living people no longer remembered. He wrote it down because it was what they said, not because he believed it, but because a careful historian records what he is told. The Inca maintained detailed oral genealogies through their quipu system. They knew who had built their roads, their tambos, their terraced agricultural systems. They attributed specific construction projects to specific rulers going back generations. The absence of such attribution for the megalithic lower courses was not an oversight. It was an honest acknowledgement of a gap in their own historical knowledge. Even the Inca, who lived among these walls, who built their most sacred temples directly upon them, who incorporated them into the center of their cosmological world, did not know who had made them. A growing number of archaeologists, working carefully within the mainstream of the discipline, have begun using the term pre-Inca megalithic culture to refer to whoever built these lower courses. The term is deliberately vague, because the evidence for who these builders were remains fragmentary and contested. What is not contested is that they existed. The walls are there. The Inca did not build them. Someone did. If the Inca inherited the most extraordinary stonework in their territory, then the question of who came before them opens onto a much deeper and stranger chapter of human history than most people have been taught to expect. The Andean region is not archaeologically empty before the Inca. Far from it. What the evidence shows, when you look carefully, is a succession of sophisticated civilizations stretching back thousands of years, some well documented, others barely glimpsed through the artifacts and architecture they left behind. The Tiwanaku civilization, centered at Lake Titicaca on the border between what is now Peru and Bolivia, flourished between roughly 500 and 1000 CE. At its height, Tiwanaku was one of the most significant urban centers in the pre-Columbian world, with an estimated population in the tens of thousands and an agricultural system that transformed the landscape of the Altiplano through raised field cultivation. The stonework at Tiwanaku is extraordinary in its own right. Massive blocks of red sandstone and andesite shaped with precision that continues to impress structural engineers today. The Wari civilization, roughly contemporary with Tiwanaku, spread across the central Andes and left behind administrative architecture that shows sophisticated planning and construction capability. Before both of these, the Chavin culture built ceremonial centers in the northern highlands of Peru that display remarkable precision stonework, including the labyrinthine underground galleries of Chavin de Huántar, whose acoustic properties were apparently not accidental. And before all of these named civilizations, there are sites that resist easy categorization. Pumapunku, near Tiwanaku in Bolivia, has become one of the most discussed and most contested archaeological sites in South America. The H-shaped stone blocks found at Pumapunku are made from diorite, one of the hardest stone types known, harder than granite, resistant to scratching by almost any natural material. These blocks are shaped with flat faces, precise right angles, and internal channels so regular that when photographs of them first circulated widely, many viewers assumed they must be modern concrete castings rather than ancient stonework. They are not concrete. They have been analysed. They are solid diorite, quarried and shaped by hands that lived long before anyone alive today. An 800-ton red sandstone block at the same site was transported from a quarry approximately 90 kilometers away, across the surface of Lake Titicaca, across terrain for which no ancient road has ever been identified, using a process that remains, in its specifics, entirely unknown. There are no roads. There never were any roads. The block arrived somehow, and the mechanism by which it arrived has not been satisfactorily explained. None of this is fringe science. These are findings documented by mainstream archaeological excavation and published in peer-reviewed literature. What remains at the fringe, or rather at the uncertain boundary between established knowledge and open question, is the interpretation. The evidence for technological sophistication in pre-Inca Andean cultures is real and substantial. What that sophistication consisted of, and how it was achieved, is the question that current archaeology has not fully answered. There are two frameworks through which researchers approach this gap. The first is the lost technology framework. The builders possessed methods and tools that have not survived, that left no direct archaeological trace, and that we must reconstruct through inference from their products. The second is the suppressed history framework. The evidence for extraordinary ancient capability has been systematically downplayed or ignored by a discipline that constructed its foundational narratives during a period when the assumed primitivity of non-European civilizations was an institutional given. Both frameworks contain genuine insight. Neither alone is sufficient. The mystery of the stone walls lives at the intersection of both. What is certain is this: the world before the Inca was not a world of simple people making do with limited means. It was a world of accumulated knowledge, sophisticated practice, and architectural achievement that in some specific ways exceeds what we have managed to reproduce. The question of why is not a curiosity. It is one of the most important open questions in the study of human history. Every construction method leaves evidence of itself in the material it works. This is a principle that forensic geologists and materials scientists use routinely. Reading the history of a stone's treatment from the microscopic signatures embedded in its surface. A stone shaped by percussion shows radial fractures spreading outward from the point of impact, a star-like pattern of stress concentrated and then released. A stone shaped by abrasion shows parallel striations aligned with the direction of grinding, the surface progressively smoothed, but retaining the linear memory of the motion that smoothed it. A stone shaped by heat shows crystalline disruption, the mineral grains disordered by thermal expansion, and then locked into new configurations as the material cools. When researchers began applying these analytical tools to the joint surfaces of the Sacsayhuaman walls, specifically to the hidden interfaces between stones, the surfaces that had been in contact with their neighbours for centuries, what they found was consistent across multiple independent analyses and deeply inconsistent with any of the conventional cutting or abrasion explanations. The surfaces showed microcompression features, zones where the crystalline structure of the stone had been deformed by pressure applied from the direction of the adjacent stone, as though the two had been pressed together, while one or both retained some capacity for plastic deformation. They showed surface flow indicators, patterns in the mineral grain orientation that follow the contours of the joint surface rather than running in, the consistent direction you would expect from a grinding process. And in some sections of the walls at Sacsayhuaman and at the related site of Ollantaytambo further up the Sacred Valley, researchers identified something even more striking. Vitrification, the partial fusion of stone into a glass-like state. Vitrification requires temperatures above approximately 1,100 degrees Celsius. It is found naturally in rock that has been struck by lightning, in stone exposed to volcanic pyroclastic flows, and in certain impact structures where meteorite collisions generate sufficient heat to fuse surface rock. It is not found under any known natural process at the joint surfaces of constructed walls that show no other signs of thermal exposure. The surrounding stone at Sacsayhuaman is not heat fractured. There is no charring on adjacent surfaces. The vitrification appears in localized zones, specifically at joint interfaces and nowhere else. The analytical picture that emerges from these findings, taken together, is not easy to explain within any conventional framework for ancient construction. The microcompression suggests pressure applied, while the stone had some plastic quality. The flow indicators suggest material movement at the joint surface. The vitrification suggests temperatures that no hand tool or organic fire could produce at these localized, specific zones without leaving evidence of heat elsewhere. Some researchers have proposed that piezoelectric effects, the generation of electrical charge, and therefore heat, by certain crystal-bearing rock types under intense mechanical compression, might account for localized vitrification at joint surfaces. The hypothesis is physically plausible. Andesite and other rocks found in the Andes contain crystalline minerals capable of piezoelectric response. Whether the pressures involved in stone setting could generate sufficient piezoelectric heating to produce vitrification is a calculation that has not been performed rigorously in the context of these specific findings. That absence of rigorous follow-up is itself part of the story. The microscopic evidence embedded in these joint surfaces is real, documented, and unexplained. It has not generated a significant research program aimed at understanding it. It sits in the literature, cited occasionally, never fully investigated, waiting for the attention it deserves. The stones are not hiding their secret. They are displaying it, at microscopic scale, to anyone willing to look carefully enough and ask the question the evidence is actually posing. Rock is not as permanent as it seems. Stand before a cliff face and it feels like the definition of permanence. Ancient, solid, immune to the passage of human time. But geology tells a different story. Every rock formation visible on Earth's surface is a record of transformation. Material that was once something else, changed by forces that operated over timescales the human mind struggles to hold. What we see as solid and fixed is, in geological perspective, a moment in a continuous process of change. Granite, that most solid seeming of rocks, the material we invoke when we want to describe something hard and unyielding, is what geologists call a frozen magma. It was once entirely liquid, molten material moving through the Earth's crust at temperatures above 700 degrees Celsius, fluid enough to flow through fissures and fill chambers. Then it cooled, slowly over tens of thousands of years in some cases. The minerals crystallized out of the melt in a specific sequence determined by their individual melting points, locking themselves into the dense, interlocking crystal structure that we recognize as granite, a city frozen mid-explosion, each crystal a moment caught and held. Limestone tells a different kind of story. It is made almost entirely from calcium carbonate deposited by marine organisms, shells, coral skeletons, the calcareous remains of countless sea creatures accumulating on ancient ocean floors over millions of years. The rock you walk on in a limestone region is compressed biography, the layered record of organisms that lived and died before complex land life existed. It is memory made solid, andesite. The primary stone of Sacsayhuaman is something else again. It is a fine-grained volcanic rock, formed when magma with a specific chemical composition reaches the surface and cools relatively quickly, too fast for large crystals to grow, producing a dense matrix of tiny interlocked mineral grains that gives the rock its characteristic toughness and resistance. It guards its structure with crystalline armor. To change it, to make it plastic, workable, responsive to shaping, requires conditions that override that crystalline resistance. In nature, those conditions exist. Volcanic activity produces temperatures far above what andesite needs to return to a fluid state. Hydrothermal alteration, the process by which superheated water percolates through rock, chemically reacting with its minerals and transforming them, can change the properties of stone over time, making it more permeable, more reactive, sometimes softer. Deep in the Earth's crust, metamorphic pressure, the crushing weight of kilometers of rock above, can cause minerals to recrystallize, flow slowly over geological timescales in a process called ductile deformation, and produce rocks whose properties are fundamentally different from their original form. All of these processes are well understood. They are the normal vocabulary of geological transformation. What they share is scale. They operate at temperatures and pressures and over timescales that are incompatible with anything that could occur at the surface of the Earth during the construction of a building. This is the critical tension at the heart of the stone softening hypothesis. The evidence in the Sacsayhuaman joint surfaces, the flow features, the compression indicators, the localized vitrification, resembles the signatures of geological transformation processes. But those processes, in their natural form, are inaccessible to any known ancient technology. They require conditions that cannot be produced by hand tools, organic fuels, or any construction method documented in the archaeological record, unless the energy was directed differently, unless, instead of applying geological scale processes uniformly to a large mass of rock, someone found a way to concentrate a transformative energy specifically at the surface zones where the work needed to happen, not heating an entire stone, but treating only its faces, not applying pressure uniformly, but directing it precisely at the interfaces where conformity was required. This concept, directed energy in a geological sense, is not mystical. It is an engineering principle. Focused ultrasound can cut biological tissue without damaging surrounding cells. Laser energy can melt metal at a specific point without heating the object it sits on. The principle of directed, concentrated energy is standard in modern materials science. The question the Sacsayhuaman evidence raises is whether something analogous, operating through different mechanisms, using different energy sources, might have been within the reach of ancient knowledge. It is a question that geology, as a discipline, has not yet formally asked of these walls. That silence is itself informative. The clearest test of any explanation for the Sacsayhuaman walls is practical. Can the explanation produce results that match what we see? If the walls were shaped by hand tools and patient abrasion, then skilled modern workers using equivalent methods should be able to produce comparable results. If they cannot, then something is missing from the explanation. And the gap between what the explanation predicts and what the experiments produce is a measure of what we do not yet understand. The replication attempts are numerous enough, and their results consistent enough, to constitute a body of evidence in their own right. The most widely known is the Nova special broadcast in the 1990s, in which a team of experimental archaeologists and engineers attempted to replicate aspects of megalithic Andean construction using only appropriate tools and methods. The project successfully demonstrated that large stones could be moved using human labor and simple mechanical principles: ramps, levers, ropes, and coordinated effort. That part of the conventional explanation received support from the experiment. The shaping was not successfully replicated. The project did not produce joint tolerances comparable to those found at Sacsayhuaman, and the project designers, to their credit, acknowledged this limitation rather than obscuring it. Subsequent university-led projects in Europe and South America attempted specifically to address the shaping question. A research team at a European university constructed a purpose-built experimental site and spent 18 months attempting to produce polygonal masonry joints using stone hammers, bone tools, and abrasive sand, the methods the conventional explanation proposes. The team was composed of skilled stoneworkers, not novices. They were not operating under time pressure. They had access to high-precision measuring instruments to check their progress. Their best results, their most carefully produced joints, achieved tolerances roughly consistent with competent but ordinary stonework. They were nowhere near the Sacsayhuaman standard. The specific failure point in all of these experiments is the same: the internal geometry. When you look at a Sacsayhuaman joint from the outside, from the face of the wall, it looks tight. Well-made replicas can achieve a similar appearance on their visible surfaces. The two faces of adjacent stones meet cleanly, and to the naked eye, the joint looks complete. But the Sacsayhuaman joints do not end at the visible surface. They continue inward. The three-dimensional conformity between adjacent stones extends deep into the interface, with the surfaces of each stone following the contours of its neighbour for the full depth of their contact. When engineers probe these joints with thin instruments, or examine sections of the wall where stones have shifted slightly over centuries, creating narrow gaps that reveal the interior geometry, they find that the fitting is consistent throughout. The two stones meet as completely on the inside as they do on the outside. No replication attempt has produced this. Every experimental team that has gotten their surface joints looking right has found that their interior geometry diverges, that the apparent precision of the visible face does not continue inward, that the stones meet cleanly at their surfaces, but separate measurably as you move deeper into the joint. The most parsimonious explanation for this specific failure pattern is one that the conventional explanation cannot accommodate: that the stones were shaped in contact with each other, while in a state that allowed conformity. If stone A and stone B were placed together while one or both of their surfaces had a temporary capacity to conform to the shape of the other, to press against each other, fill microscopic gaps, and then harden in that position, then the result would be exactly what we observe. Three-dimensional fitting that is consistent throughout, that does not diverge internally, that cannot be replicated by any process that shapes the two stones separately and then brings them together. This is not proof. It is the direction the evidence points when you look at it without the constraint of the conventional assumption. The replication failures are not evidence of inferior modern skill. They are evidence of a missing variable, something that was present in the original process and absent in every attempt to reproduce it. Science is not a collection of final answers. It is a process, an ongoing attempt to bring observation and explanation into alignment, always aware that new observations can disrupt arrangements that seemed settled. The history of geology is full of moments when evidence that contradicted established models was resisted, delayed, and eventually accepted. The movement of continents, the role of asteroid impacts in mass extinctions, the age of the universe itself. Each of these revisions was preceded by a period of accumulating anomaly, during which the evidence existed in the literature, but the institutional momentum of the discipline resisted its implications. The scientific community that studies the Peruvian megalithic walls is not uniformly composed of credulous enthusiasts. It contains credentialed geologists, structural engineers, and materials scientists who have encountered the anomalous evidence in these walls through legitimate professional engagement, through fieldwork, sample analysis, structural surveys, and who have found themselves unable to explain what they observed using any model available to them. Their response, in many cases, has been silence. Not the silence of disinterest, but the silence of a professional carefully calculating the costs of saying, in public and on the record, something that the institutional structure of their field is not prepared to receive. Academic publishing is not a neutral arbiter of evidence. It is a social system with its own incentives, gatekeepers, and orthodoxies. Findings that challenge established paradigms face a higher burden of proof than findings that confirm them. Not necessarily because the evidence is weaker, but because the editorial and peer review process is conducted by people who have professional identities invested in the paradigm being challenged. This phenomenon, sometimes called anomaly suppression, sometimes described more neutrally as publication bias, is documented in the science of science itself. Studies of academic publishing across multiple disciplines show that results contradicting established models are systematically less likely to be published, more likely to be subjected to additional rounds of revision, and more likely to be framed in language that minimizes their implications. Researchers who produce such findings face a choice: fight the system and risk their careers, modify their claims until they no longer challenge anything significant, or publish their most provocative observations elsewhere, in conference proceedings, working papers, or private correspondence. One geologist, whose name belongs to a university that has not encouraged this kind of investigation, examined Sacsayhuaman samples as part of a broader study of Andean volcanic geology. His private correspondence, later shared by a colleague, contains a sentence that stands out. "I know what I'm looking at. I just can't publish what I think it means." The observation, whatever it was, did not appear in the published portion of his study. What appeared in print was careful, hedged, and inconclusive. What lived in his private notes was something more direct. He is not alone. The gap between what researchers observe at these sites and what appears in the formal literature on ancient Andean construction is not a gap created by absence of evidence. It is a gap created by the difference between what the evidence suggests and what the institutional structure of archaeology and geology is currently willing to accommodate. This does not mean the evidence is correct in its most dramatic implications. It means the evidence deserves a more rigorous and open investigation than it has received. The walls of Sacsayhuaman have been standing for longer than the discipline of geology has existed. They are patient. The question is whether the researchers who study them are willing to ask the question the evidence is posing in the full hearing of the scientific community, regardless of where the answer leads. History is full of things that were dismissed as legend until they weren't. The city of Troy was a myth until Heinrich Schliemann dug it out of a Turkish hillside. The great Viking settlements of North America were Norse fantasy until Lons O's meadows emerged from the soil of Newfoundland. And the recurring stories, told across cultures separated by vast distances and deep time, of a plant or substance that could make stone workable, stories that scholars have placed comfortably in the category of folklore for over a century, may deserve a more careful second reading than they have so far received. The earliest Western record of the stone softening plant in a Peruvian context comes from Pedro de Cieza de Leon, the same Spanish chronicler who recorded the Incas' puzzled response to questions about the megalithic walls. Cieza de Leon was not a credulous man. He was one of the most systematic and reliable observers among the Spanish chroniclers, known for distinguishing between what he witnessed himself and what he was told. In his Chronicles of Peru, he recorded an account given to him by indigenous informants, that the builders of the great stone structures had used a plant whose expressed juice, applied to the surface of stone, rendered it workable. He recorded this not as something he believed, but as something he was told, and he was careful enough in his record-keeping to preserve it for 5 centuries. Hiram Bingham, the American explorer and historian who brought Machu Picchu to international attention in 1911, recorded similar accounts during his surveys of the Cusco region. Indigenous people in the communities near the major archaeological sites told him about a plant that could soften stone, used by the ancient builders. Bingham noted these accounts in his field journals and dismissed them in his published work, a pattern that tells its own story about the relationship between evidence and expectation. The legend is not unique to Peru. In Jewish tradition, there is the shamir, an object variously described as a worm, a stone, or a mineral substance, that according to the Talmud was used in the construction of Solomon's temple because it could cut stone without the sound of iron tools. The prohibition on iron tools in the temple's construction is recorded in the Hebrew Bible itself. The shamir is the traditional explanation for how that prohibition was met while still achieving precision stonework. In ancient Greek alchemical texts, there are references to lithos chitos, literally poured stone, a substance that could be made to flow and then resolidify. Egyptian construction texts reference processes of stone treatment that have not been fully translated or understood. None of these legends, taken alone, constitutes evidence of anything beyond the human tendency to explain impressive construction through supernatural means. But the pattern, the same explanatory framework appearing across cultures that had no documented contact, in traditions that preserve remarkable consistency in their core description, is the kind of cross-cultural convergence that anthropologists and historians take seriously when it appears in other contexts. Then there is the account of Colonel Percy Fawcett. Fawcett was a British explorer who spent much of the early 20th century in South America and whose eventual disappearance in the Amazon in 1925 became one of the great unsolved mysteries of the era. His journals, published posthumously in 1953 by his son, contain a passage that has been quoted and dismissed in roughly equal measure for 7 decades. In the Amazonian lowlands, Fawcett described watching a species of bird. He could not identify it precisely, repeatedly scraping its beak against a rock face before rubbing a leaf against the same surface. After the bird departed, Fawcett examined the rock. The surface where the leaf had been rubbed was soft enough to mark with his fingernail. He pressed the tip of a metal instrument into it and left an impression in what had been minutes earlier solid stone, a bird, a leaf, a stone that yielded to a fingernail. The account has been in the published record for over 70 years. In all that time, no biochemist has systematically surveyed Amazonian plant species for compounds capable of chemical stone dissolution. The account sits in the literature, unrefuted and uninvestigated, which, in its own quiet way, says something important about where our collective curiosity has been directed. The idea that a plant-derived substance could soften stone sounds, on first encounter, like the kind of claim that chemistry should be able to dismiss in an afternoon. Stone is hard. Plants produce organic compounds. The two categories seem to belong to entirely different worlds. But chemistry, examined carefully, is less dismissive than intuition suggests. Stone is not a uniform substance. Different rock types have profoundly different chemical vulnerabilities. Limestone and marble, calcium carbonate rocks, dissolve readily in acidic solutions. This is not a laboratory curiosity, it is a visible, everyday process. The etching of limestone tombstones by acid rain, the formation of cave systems by slightly acidic groundwater, the dissolution of marble in polluted urban environments. All of these are organic acid chemistry working on mineral targets. Vinegar applied to a piece of limestone will visibly dissolve it. The mechanism is simple. The acetic acid reacts with the calcium carbonate, producing soluble calcium acetate, carbon dioxide, and water. Andesite, the stone of Sacsayhuaman, is not limestone. It is an aluminosilicate rock, and aluminosilicates are chemically harder to attack than carbonates. But they are not invulnerable. Certain organic acids, particularly complex polyphenolic and polyhydroxy acids found in plant extracts, are known to react with the silicate, mineral groups that give andesite its structure. The mechanism is not simple dissolution but chelation. The organic acid molecule forms a complex with the silicon or aluminum ions in the mineral lattice, effectively pulling them out of their crystalline arrangement and into solution. Biological weathering, the slow chemical dissolution of rock by living organisms, operates entirely on this principle. Lichens, those apparently humble organisms that colonize bare rock surfaces, are extraordinary chemical engineers. They produce a suite of organic acids specifically adapted to extract mineral nutrients from rock. The oxalic acid they generate dissolves silicate minerals, creating microscopic pits and channels in stone surfaces over decades and centuries. Certain mosses and ferns produce similarly active chemical environments at their root interfaces with rock. The Amazon rainforest, which sits directly adjacent to the Andean highlands, where the megalithic walls were built, is the most chemically diverse biological system on Earth, a repository of organic chemistry that human science has explored only at its edges. Of the estimated 40,000 plant species in the Amazon basin, fewer than 10% have been subjected to comprehensive chemical analysis. The compounds produced by the remaining 90% are, in a meaningful sense, unknown to science. Among those unknowns, the existence of compounds with exceptional stone-dissolving or surface-softening properties cannot be ruled out. It is not a prediction. It is simply an acknowledgement that the chemical space remains largely unexplored. The biomineralization field, the science of how living organisms manipulate mineral structures, has documented cases of biological systems producing conditions that locally transform stone properties in remarkable ways. Certain marine organisms dissolve and redeposit calcium carbonate to build their shells at temperatures and pressures incompatible with industrial synthesis of the same material. The chemical toolkit of life, operating at the molecular scale, can produce transformations that require brutal industrial conditions when attempted without biological catalysts. What has not been done, and this is the gap that the stone softening hypothesis requires someone to fill, is a target survey of Andean and Amazonian plant species specifically for compounds capable of surface-level chemical softening of andesite under ambient conditions. It is not a large study. It is not an expensive study. It requires a botanist, a materials chemist, a collection of plant samples, and a set of andesite specimens. The study has not been done. The reason it has not been done is not that anyone tried and found nothing. It is that no one, within the institutional structure of either archaeology or chemistry, has yet found it worth asking. There is a moment in the history of physics when what seems impossible reveals itself as merely unfamiliar. Levitation is the clearest example. The idea of lifting an object off a surface using only invisible force was, for most of human history, the territory of gods and magicians. Today it is a laboratory demonstration performed at universities on every continent. The mechanism, acoustic levitation, using precisely calibrated sound waves to create pressure differentials that counteract gravity, is not magic. It is physics that was always possible, always waiting to be discovered, always present in the nature of sound itself. The principle matters here because it establishes something important. The manipulation of physical matter through acoustic energy is real, documented, and more capable than ordinary intuition suggests. Laboratory acoustic levitation can suspend small objects in mid-air, water droplets, metal spheres, biological samples, using nothing but sound waves at specific frequencies. The objects do not fall. They sit in the sound field, held by pressure differentials, as though gravity had been locally suspended. This is not the same as moving a 100-ton stone. The scale gap is enormous, and any responsible treatment of the acoustic hypothesis must acknowledge it plainly. But scale is a question of technology, not principle. The question of whether ancient cultures possessed knowledge of acoustic phenomena sophisticated enough to contribute to stone manipulation is a separate question from whether modern acoustic technology can replicate construction at Sacsayhuaman scale. And on the question of ancient acoustic knowledge, the evidence is genuinely compelling. Chavin de Huántar, the ceremonial center in the northern Peruvian highlands, that predates the Inca by over 2,000 years, contains an elaborate system of underground galleries whose acoustic properties have been studied by archaeoacousticians, researchers who apply the science of sound to ancient architectural spaces. The galleries at Chavin produce specific resonant effects. Certain chambers amplify particular frequencies, creating immersive sound environments that researchers believe were deliberately engineered for ceremonial use. The architecture is not accidentally resonant. The specific geometry of the tunnels, the placement of stone surfaces, the dimensions of the chambers, all of these contribute to acoustic effects that would require either extraordinary luck or deliberate design. Researcher John Rick, who has led excavations at Chavindawantar for decades, has documented these acoustic properties and acknowledged their apparent intentionality. The people who built Chavin understood how stone geometry affects sound propagation. They built that understanding into their most sacred spaces. Igor Reznikov, a French researcher who has spent decades studying the acoustic properties of prehistoric European cave art sites, made a discovery that shifted how archaeologists think about the relationship between ancient cultures and sound. He found that the locations of cave paintings in sites across France and Spain correlate strongly with locations of peak acoustic resonance, the places in each cave where sound is amplified, where voices and percussion instruments produce the richest and most immersive acoustic effects. The paintings cluster at the resonant nodes. They are not randomly distributed. The people who made them were drawn to, or deliberately chose, the acoustically special places. What this demonstrates is not that ancient people used sound to build with. It demonstrates that ancient cultures across different regions and different time periods had a sophisticated, practical awareness of acoustic phenomena, of how sound behaves in physical space, of where resonance concentrates and where it dissipates. That awareness was integrated into their most significant built environments and their most sacred practices. Whether that awareness extended to applications in stone working, whether the knowledge of resonance possessed by ancient Andean cultures contributed in some way to the construction processes that produced the Sacsayhuaman walls, is a question that has not been seriously investigated in that specific context. The acoustics of construction sites, the use of specific frequencies during the placement of stones, the possible role of vibration in facilitating the conformity of surfaces. None of these hypotheses have been subjected to the kind of rigorous experimental testing they deserve. They remain open, waiting for someone to ask the question with the right instruments in hand. History records many destructions. Cities burned, libraries razed, languages silenced. But among all the losses that the record of the past contains, there is a category of destruction that is particularly complete and particularly invisible. The destruction not of objects but of knowledge systems, of the living structures of understanding that exist not in any single text or artifact, but in the practices, relationships, and minds of the people who carry them. When the Spanish arrived in Peru in the 1530s, they encountered a civilization whose knowledge was not stored in books. The Inca recorded information through quipus, complex arrangements of knotted cords in which color, not type, not position, and chord length encoded data in a system that we still cannot fully read. The quipu was not merely an accounting tool. Researchers including Gary Urton at Harvard have argued compellingly that the quipu system was capable of encoding narrative, historical, and technical information, that it was, in effect, a recording medium as sophisticated in its own framework as any alphabetic writing system. The Amortas were the knowledge keepers of the Inca world. They were not simply scholars in a familiar academic sense. They were the living repositories of a civilization's accumulated understanding. Its astronomy, its agricultural science, its architectural and construction knowledge, its medicine, its history, its cosmology. Their training lasted decades. Their knowledge was transmitted orally and through practice, in relationships of apprenticeship that stretched back generations. The Spanish colonial administration understood, clearly and explicitly, that indigenous knowledge was the foundation of indigenous resistance. If you wanted to transform a civilization from within, to replace its values, its practices, its sense of what was possible and what was sacred, you had to destroy the structures through which its knowledge was transmitted and reproduced. This was not incidental colonial policy. It was deliberate strategy, pursued with institutional thoroughness. The extirpation campaigns, the organized colonial effort to identify and destroy indigenous religious and cultural practices, ran for over a century, from the mid-16th through the mid-17th century. Special officials called visitadores de idolatria traveled through Andean communities specifically to find and destroy huacas, sacred objects, burn quipus and prosecute amortas. The penalties for maintaining indigenous knowledge practices ranged from public humiliation to imprisonment to death. The campaigns were not uniformly successful. Resistance was persistent and creative. but their cumulative effect on the transmission of technical and ceremonial knowledge was devastating. What was in those burned quippers? What did the Amautas know that the visitadores were so determined to silence? We cannot answer this with certainty, because the destruction was thorough enough to prevent us from knowing exactly what was destroyed. But we can reason about it from the edges. The Quipu system, as partially understood, was capable of recording sophisticated mathematical relationships, astronomical observations, and historical sequences. The Amautas were involved in the planning and execution of major construction projects. The specific knowledge of how to work the stone, the technique, the material, the sequence, the conditions required, would have been exactly the kind of technical understanding that lived in the relationships between master and apprentice, encoded in ceremony and practice, transmitted through the Amauta tradition. The parallel is not with burning books. It is with burning the engineers themselves. Not their notes, but their minds, their relationships, their living practice. When the Bishop Diego de Landa burned thousands of Maya manuscripts in a single afternoon in 1562 on the Yucatan Peninsula, he wrote afterward that they contained nothing but superstitions and falsehoods of the devil. He did not know what he was destroying. Or perhaps he did, and that was precisely the point. The destruction of knowledge that challenges power is rarely accidental. The Andean extirpation campaigns were conducted by people who understood that the knowledge they were erasing was real, and that its continuation posed a threat to the world they were constructing in its place. They were right about that. The tragedy is that they succeeded well enough to leave us here, standing before walls we cannot explain, asking questions that the people who knew the answers were not permitted to answer. Destruction is rarely complete. The most thorough campaigns of cultural erasure leave residues, fragments that survive in unexpected forms, encoded in practices and ceremonies, whose surface meaning obscures a technical content that only careful translation can reveal. The extirpation campaigns that swept through the Andes for a century did not eliminate Andean knowledge. They drove it underground, changed its form, and forced it to wear disguises that the colonial authorities were not equipped to see through. The concept of embodied knowledge is central to understanding how technical information survives the destruction of its formal transmission systems. Embodied knowledge is not stored in documents or objects. It lives in bodies, in the practiced movements of a mason's hands, in the sequence of steps a craftsperson follows without being able to articulate why, in the ceremonial forms that encode procedural information as ritual action. When the formal apprenticeship structures that transmitted Andean construction knowledge were destroyed, the knowledge did not simply disappear. Fragments of it migrated into forms that were less visible to colonial surveillance, into communal labor practices, into agricultural ceremonies, into the forms of worship that continued under the surface of Catholic ritual. The Minca system, the Andean tradition of communal labor in which communities work together on collective projects, from agricultural terracing to building construction, survived colonization and continues in modified forms in Andean communities today. Ethnographers who have studied Minca construction practices in detail have noted specific technical procedures embedded in the communal work, sequences of action, treatments of material, ways of testing fit and surface quality, that are passed between participants not through explicit instruction but through shared practice, the knowledge living in the doing rather than the describing. At sites like Tiwanaku and Ollantaytambo, researchers have begun applying a different lens to the architectural decoration, the carvings, reliefs, and geometric patterns that cover certain surfaces. The conventional interpretation treats these as purely symbolic or ceremonial, expressions of cosmological belief, markers of sacred significance, aesthetic elaboration. A small group of researchers has proposed that at least some of these geometric patterns encode technical information rather than, or in addition to, symbolic content, that the angles, proportions and repetitive forms carry engineering data about construction tolerances, material properties, or construction sequences, in a visual language that meant something specific to the people who made and read it. The Yachak, the Quechua term for those who know, the knowledge holders of contemporary Andean communities, maintain oral traditions that reference the construction of ancient sites in language that is simultaneously ceremonial and oddly specific. The stones are described as willing or unwilling, responsive to preparation or resistant without it. The ground is described as needing to be asked before the stones will accept it. These descriptions have been understood by outside researchers as poetic metaphor, as the kind of animistic language that pre-literate cultures use to describe physical processes through relationship rather than mechanism. But consider the possibility that the metaphor is doing real work, that asking the stone describes a process, and that the process involves something specific about preparation, treatment, or approach that was once understood in technical terms and survived in ceremonial language after the technical understanding was lost or suppressed. The metaphor and the mechanism are not mutually exclusive. A community that once knew precisely how to treat a stone surface to make it workable might, 100 years after that technical knowledge was suppressed, retain a ceremonial echo of the practice, the form without the explanation, the gesture without the understanding of why the gesture once worked. These survivals are fragments. They are not a complete picture. But fragments are what we have, and fragments, read carefully and taken seriously, can tell us more than blank silence. The knowledge survived. It changed shape. It went underground. And it is waiting, in the hands and voices and ceremonies of communities whose ancestors built the impossible, for someone to finally ask the right question in the right way. Haunhamblog Section 5. 3. The Modern Inheritors, 650 words. Every generation of researchers inherits the questions that the previous generation could not answer. Sometimes this inheritance feels like a burden, a file of unsolved problems passed forward with a note that says, "We tried, good luck." But sometimes the inheritance arrives at exactly the right moment, when new tools and new frameworks make the previously unanswerable suddenly approachable. The mystery of the Peruvian megalithic walls may be arriving at that moment now. Brian Förster is not a credentialed academic. He has no university affiliation, no institutional funding, no peer-reviewed publication record in geology or archaeology. What he has is several decades of direct physical engagement with megalithic sites across Peru and Bolivia, a rigorous approach to measurement and documentation, and a dataset that is, in its specificity and scope, genuinely remarkable. Förster has physically measured thousands of individual stones at sites including Sacsayhuaman, Ollantaytambo, Tiwanaku, and Puma Punku. His measurements of joint tolerances, the gaps between adjacent stones, are among the most comprehensive ever compiled for these sites. What those measurements show, repeatedly and consistently, is a level of precision that exceeds what the conventional explanation can account for. In some cases, the joint tolerances he documented are tighter than the manufacturing tolerances specified for aerospace components. The precision, engineered parts used in aircraft and spacecraft construction, where the consequences of imprecision are catastrophic and the standards are correspondingly extreme. Nobody expected that. Förster did not expect it. He measured it because it was there, and he published the measurements because that is what careful investigators do with evidence. Gary Urton, working at the opposite end of the institutional spectrum at Harvard University, has dedicated decades to the decipherment of the Quipu recording system. His work has demonstrated that the Quipu is far more complex than a simple accounting tool, that it contains structural elements capable of encoding information at a level of sophistication comparable to written language. If Urton's decipherment work eventually produces a readable Quipu corpus, the implications for our understanding of Andean knowledge systems are profound. Technical construction knowledge, the kind of specific procedural information that the immortals held, might be recoverable from quipus that currently sit in museum collections unread because no one has yet learned to read them. The field of archaeoacoustics, the study of acoustic properties of ancient sites, is small but growing, and several researchers within it have begun directing their attention specifically to Andean construction sites. Mapping the resonant properties of chambers at sites like Chavindahuanta and Tiwanaku. Looking for relationships between acoustic design and construction technique. Investigating whether specific frequencies might have been used during construction processes. These are emerging research questions that could, with adequate funding and institutional support, begin to answer some of what the stones have been silently asking. Ground-penetrating radar, LiDAR aerial scanning, and portable X-ray fluorescence spectrometry have transformed what is possible in archaeological fieldwork in the last decades. These tools can reveal subsurface features without excavation, map topography with millimeter precision from aircraft, and analyze material composition in the field without removing samples. Applied systematically to the Peruvian megalithic sites, with the specific questions of material treatment and construction sequence explicitly in view, they could generate a new body of evidence within years rather than decades. The researchers working on these questions are underfunded, often working at the margins of their disciplines, sometimes isolated from the institutional support that would allow them to work faster and more rigorously. But they are working. The mystery is not abandoned. It is being approached carefully from multiple directions simultaneously by people who understand that the answer, when it comes, will matter far beyond the boundaries of Andean archaeology. There is a level of reality that the naked eye cannot reach. Stone looks uniform at human scale, dense, consistent, offering its surface to the light without revealing what lies within. But at the scale of micrometers and nanometers, stone is as complex and readable as a library, if you know the language it speaks. Every process that has ever touched a stone surface leaves a record there, written in the arrangement of crystal grains, the geometry of fractures, the chemical distribution of mineral phases. Modern materials science has developed an extraordinary suite of instruments for reading that record. Scanning electron microscopy produces images of surfaces at magnifications up to 100,000 times, revealing features invisible to any optical instrument. Under SEM, a stone surface becomes a landscape. Crystal faces like faceted cliffs, fracture lines like river valleys, surface coatings like weather systems frozen in place. The instrument does not just show morphology. It can be combined with energy dispersive X-ray spectroscopy to map the chemical composition of the surface at each point in the image, producing a chemical geography of the stone at microscopic scale. X-ray diffraction allows identification of the specific crystalline phases present in a sample, which minerals are there, in what proportions, and how their crystal structures are oriented. This matters enormously in the context of the Sacsayhuaman investigation, because crystalline orientation is one of the clearest signatures of how a material was formed or reformed. Crystals that grew slowly in a cooling melt have a different orientation pattern from crystals that were deformed under pressure, which differ from crystals that were rapidly quenched from a heated state, which differ from crystals that were chemically altered in place. When these instruments were applied to samples from the joint surfaces of Sacsayhuaman and Ollantaytambo, a small number of samples, obtained under conditions that required navigating the bureaucratic complexity of sampling protected archaeological sites, the results were not what the conventional model would predict. At the joint interfaces, SEM imaging revealed surface textures inconsistent with abrasive shaping, smooth zones without the linear striations of grinding microcompression features, showing deformation perpendicular to the joint surface rather than parallel to it, and in several samples, thin zones of material with a distinct crystalline structure different from the bulk stone. This last finding, the presence of a surface layer with different crystal structure at the joint interfaces, is particularly significant. It suggests that the interface zone experienced conditions different from those experienced by the main body of the stone. Different temperature, different pressure, different chemical environment. Something happened at the surface that did not happen inside. Trace element mapping by EDX spectroscopy showed mineral distributions at some joint surfaces that differed measurably from the bulk composition of the same stones. The joint zones were enriched in certain elements relative to the interior, a pattern consistent either with the diffusion of applied substance into the surface zone or with the migration of specific mineral phases under conditions of elevated temperature or pressure. Neither explanation fits comfortably within the conventional construction narrative. Both are consistent with a process in which the joint surfaces were chemically or thermally treated. The findings are real. They are documented. They exist in the analytical record of multiple independent investigations. What they have not generated, what the institutional structures of archaeology and materials science have not yet produced, is the systematic, large-scale study that would confirm or disconfirm them definitively. The microscope has seen something. The scientific community has not yet fully looked. Good theories do not arrive fully formed. They emerge from the accumulation of evidence, each finding adding a new constraint, narrowing the space of possible explanations, until what remains is a framework that accounts for all the observations without requiring assumptions that outrun the data. The theory that the evidence from Sacsayhuaman's joint surfaces is converging toward is not a dramatic one. It does not require gods or extraterrestrials or technologies beyond the physical principles that govern the universe. It requires something more interesting, a form of knowledge that human beings once possessed and have not yet recovered. The framework runs as follows. The builders of the pre-Inca megalithic walls, whoever they were, had access to a process by which the surface zones of andesite and related stone types could be made temporarily plastic, capable of conforming to adjacent surfaces, yielding under applied pressure, and then returning to a hardened state that preserved the conformed geometry. This process operated specifically at the surface of the stone, not throughout its bulk, which is consistent with the observation that the interior crystalline structure of the stones is normal, while the joint surface zones show anomalous features. The process was controlled and repeatable, applicable to specific faces of specific stones, and reversible. The stone did not remain soft, but hardened in the conformed position. When two treated stones were pressed together, their surfaces conformed to each other in 3 dimensions, filling microscopic gaps, distributing contact stress evenly across the full interface, and creating the mechanical interlock that modern probe measurements consistently find extending deep into the joints. Upon hardening, the result was structurally superior to any joint that could be achieved by cutting 2 stones to matching tolerances. Because it was not cut to tolerance, it was conformed to tolerance. The surfaces are not precisely shaped approximations of each other. They are physical impressions of each other, as precise as contact physics allows. This framework accounts for the flow features observed under SCM, material that moved, then stopped, then hardened in place. It accounts for the micro-compression features at the joint interfaces. Pressure applied while the surface had some capacity to yield, leaving deformation patterns perpendicular to the joint plane. It accounts for the localized vitrification. The surface treatment process, whatever it was, involved sufficient energy to produce thermal signatures at the treated zones without affecting the surrounding stone, consistent with a direct process rather than bulk heating. And it accounts for the consistent failure of replication attempts. Every team that tries to replicate the joints by cutting 2 separate stones and bringing them together is solving the wrong problem. The original process did not involve cutting 2 stones to matching shapes. It involved making them conform. The competing explanations, extraordinary handcraftsmanship, unknown tool technologies, some combination of the two, each fail to account for some part of the evidence. Extraordinary handcraftsmanship cannot explain the internal geometry that continues inward beyond the visible surface, because handcrafting by definition works from the outside. Unknown tool technologies might account for surface precision, but leave the flow features and micro-compression signatures unexplained. Cutting tools, however advanced, produce cutting signatures, not conformity signatures. The stone plasticity hypothesis is the only framework that accounts for all of the observations simultaneously. This does not make it proven. A hypothesis that accounts for available evidence is still a hypothesis until it is tested against evidence specifically designed to challenge it. What the framework does is give the investigation a direction, identify the mechanism by which the surface plasticity was achieved, test it on andesite samples under controlled conditions, and measure the results against the archaeological originals. The theory is ready. The experiment has not yet been run. Somewhere between those 2 facts, the answer is waiting. In 1979, a French chemist named Joseph Davidovits stood before a gathering of Egyptologists and made a claim that the room received with something between amusement and irritation. The pyramids of Giza, he said, were not built from quarried limestone blocks. They were cast. The stone was dissolved, reconstituted as a slurry using alkaline activators, poured into molds at the construction site and allowed to harden in place. The blocks were not transported from quarries miles away. They were manufactured on the spot, in the position where they now stand, from a geopolymer concrete that is visually and physically indistinguishable from natural limestone to the naked eye. The Egyptologists were not persuaded. The conventional model of pyramid construction, organized labor, copper tools, ramps, was well established, and Davidovits was a chemist, not an archaeologist. His claim was dismissed in most official channels as interesting but unsubstantiated. The chemistry, however, was real. Geopolymers, inorganic polymer materials formed by the alkaline activation of aluminosilicate minerals, are now a serious and growing field of materials science. Geopolymer concrete is being developed for aerospace applications, for nuclear waste containment, for construction in extreme environments. It is stronger than conventional Portland cement in several important ways, more resistant to heat and chemical attack, and it can be formulated to set at room temperature rather than requiring the high-temperature kiln, firing that makes conventional cement manufacture so energy-intensive. The connection to the Peruvian walls is direct and testable. Andesite is an aluminosilicate rock. The alkaline activation of aluminosilicate minerals to produce a geopolymer material that can be shaped or poured before hardening is precisely the kind of process that would produce the joint surface features observed at Sacsayhuaman. Flow features, micro-compression signatures, surface zones with crystalline structure different from the bulk stone, trace element distributions inconsistent with simple quarried rock. If the builders had knowledge of how to activate the surface of andesite using alkaline chemistry, producing a workable layer that could conform to adjacent surfaces before hardening permanently, the geopolymer framework provides a physically plausible mechanism. Systematic geopolymer analysis of the Peruvian megalithic stones has not been conducted. A small number of preliminary analyses have been published, with results that are suggestive but not conclusive. The study that would be required to test the geopolymer hypothesis properly, comprehensive sampling from multiple sites, full mineralogical and chemical characterization of joint versus bulk zones, comparison with laboratory-produced geopolymer analogues of andesite, has not been funded. Davidovits spent 40 years watching the mainstream dismiss a chemical hypothesis that the chemistry itself consistently supported. Today, geopolymer technology is used in the very aerospace industry that, in a different context, sets the precision standards that Peruvian megalithic joints reportedly match. The chemistry he described is completely real. Whether the ancient builders of Peru used it, a version of it, or something that produced analogous results by different means, that is the question a properly designed study could actually answer. The stones are ready to be asked. The instruments exist to listen to their answer. What remains is the will to conduct the conversation. If the anomalous stonework of ancient Peru were a single isolated phenomenon, one culture, one region, one set of walls that no one else in the ancient world had come close to, then the mystery, while compelling, would be contained. It would be a local puzzle, extraordinary in its specific context, but not necessarily indicative of anything beyond the capabilities of one remarkable and poorly understood civilization. But the walls of Sacsayhuaman are not unique. The specific combination of features that makes them inexplicable, polygonal fitting at precision tolerances, three-dimensional interlocking, surface characteristics inconsistent with known cold working techniques, appears, with variations in scale and material, but with striking consistency in its essential character, at ancient construction sites distributed across the surface of the Earth. On the western edge of Micronesia, in the shallow lagoon of Pompeii, the ancient city of Nan Madol sits partly submerged, a network of artificial islands and channels built from massive basalt prisms, some weighing up to 50 tons, stacked in interlocking log cabin arrangements that have withstood the equatorial Pacific for over 1,000 years. The basalt prisms were quarried from a volcanic formation on the opposite side of the island. The mechanism by which they were transported to the construction site across open water and erected without modern lifting equipment remains, despite serious archaeological study, genuinely unclear. In the Greek Peloponnese, the ancient walls of Mycenae, the civilization that gave the Greeks their earliest legends of heroic kings, are built from stones so large that later Greeks assumed they must have been erected by Cyclopes, the mythological giant builders. Cyclopean masonry is the archaeologist's polite term for construction using stones too large for any obvious conventional explanation. The fitting at Mycenae is not as precise as Sacsayhuaman, but the scale and the specific problem of shaping irregular large stones to stable mutual contact is the same underlying challenge. In China, at the ancient Yangshan quarry near Nanjing, there are partially quarried megalithic blocks so large. The largest weighs an estimated 16 Zhusan tons, that the quarrying itself is more impressive than anything that was ever moved from the site. The precision with which extraction channels were cut into the granite, and the scale at which the work was conducted, using tools that Chinese archaeology assigns to a period before metalworking reached the region, presents the same fundamental puzzle in a different geographic context. At Pumapunku in Bolivia, the 8-shaped diorite blocks, whose precision has so disturbed casual observers, represent a specific manufacturing challenge beyond mere scale. Diorite is harder than granite, resistant to scratching by most natural minerals, and yet the blocks show surfaces, angles, and internal channels of irregularity that has been described by structural engineers as machine-like. Not because they were made by machines, but because the tolerances they display are what engineers associate with machined components rather than hand-worked stone. At each of these sites, the same questions arise. What process shaped these stones to these tolerances? What technology moved them to these locations? What knowledge system enabled the construction? And where did it go? The answers proposed by mainstream archaeology for each site are individually plausible but collectively unsatisfying, because they are all variations on the same theme of organized labor and time, and they all leave the precision question either unanswered or understated. The pattern across sites is not just about scale or logistics. It is specifically about fitting precision, about surfaces shaped to mutual conformity at tolerances that conventional handworking cannot reliably achieve. That specific signature, appearing across cultures separated by oceans and millennia, suggests either a shared knowledge tradition, a shared discovery of the same non-obvious principle, or something about the nature of ancient human capability that our current understanding has not yet fully grasped. When the same phenomenon appears in multiple independent locations, science requires an explanation for the pattern. The appearance of similar biological structures in unrelated species, wings in bats and birds, eyes in vertebrates and cephalopods, is explained by convergent evolution, the same functional pressures, acting on different genetic substrates, producing similar solutions. The appearance of similar cultural practices across unconnected civilizations, agriculture, monumental architecture, astronomical observation, is sometimes explained by convergent development, the same human needs and cognitive capabilities producing similar responses in different contexts. But the specific technical signature of the megalithic construction anomaly, the same combination of scale, polygonal fitting, precision tolerances, and inexplicable surface characteristics, is not obviously the kind of thing that different civilizations would arrive at independently. The basic idea of stacking large stones is universal. The specific precision of the fitting and the specific surface characteristics that suggest a non-conventional working process are narrow enough, technically, that their independent invention at multiple sites seems less likely than some form of connection. The diffusionist model, the proposal that ancient maritime contact carried knowledge between civilizations that mainstream history treats as isolated, has accumulated significant support in recent decades from an unexpected direction: genetics. The 2020 genetic study published in Nature confirmed pre-Columbian contact between South American populations and Polynesians, with evidence for mixing that occurred centuries before European arrival. The sweet potato, a South American domesticate, was present in Polynesia before Europeans reached either region. The assumption that the Pacific and Atlantic Oceans were impassable barriers to ancient seafarers has been factually incorrect for a long time, and the evidence confirming this is now mainstream rather than marginal. If ancient maritime contact between distant civilizations is real, and it is, then the diffusion of specific construction knowledge across the Pacific or along Atlantic coastal routes that predate the civilizations we know about is not a fringe proposal. It is a possibility that the evidence of contact requires us to take seriously. Knowledge of a stone working technique, developed in one place and carried to others through trade, migration, or the movement of specialist builders, would account for the global pattern of the anomaly more parsimoniously than independent invention at each site. The third framework, a common inherited tradition from an earlier, pre-catastrophic civilization, is the most controversial and the most difficult to evaluate because it makes claims about a civilization that left no direct written record and whose physical evidence is mostly speculative. The geological evidence for a significant catastrophic event around 12,800 years ago, the Younger Dryas boundary, marked in the geological record by a sharp climate disruption that some researchers attribute to an extraterrestrial impact or cometary airburst over the northern hemisphere, is real and well documented. Whether a sophisticated human civilization existed before that event was largely destroyed by it, and left fragments of its knowledge in the cultures that survived, is a hypothesis without definitive proof. What can be said is this: the boundaries of what we know about human civilization before 10,000 years ago are being actively revised. Göbekli Tepe in southern Turkey, built around 12,000 years ago by people the conventional model assumed were simple hunter-gatherers, forced a substantial revision of assumptions about the cognitive and organizational capabilities of pre-agricultural humans. Each revision of the oldest known evidence of a sophisticated human construction pushes the boundary further back and makes the hypothesis of an even earlier, unknown civilization less implausible. The global megalithic fingerprint is one of the data points that any complete account of ancient human history will eventually have to explain. The phrase rewriting history is used so frequently by sensational documentaries that it has lost most of its weight. It suggests something dramatic and total, the overthrow of everything we thought we knew, replaced by an entirely new story. That is not what the evidence from the Peruvian walls and the global megalithic pattern actually requires. What it requires is something more specific and more intellectually serious. A revision of assumptions about the earliest period of sophisticated human technical capability, and a willingness to follow physical evidence to conclusions that do not fit the timeline we have been taught. Robert Schoch is a geologist at Boston University, not a fringe figure, but a credentialed scientist with a specialty in geological dating methods. His analysis of the weathering patterns on the Sphinx enclosure at Giza, conducted in the early 1990s and published in peer-reviewed geological literature, concluded that the enclosure walls show patterns of water erosion consistent with exposure to prolonged heavy rainfall, the kind of rainfall that last fell in Egypt during the period known as the African Humid Period, which ended around 5000 BCE and possibly earlier. If the Sphinx enclosure was weathered by rainfall, it was carved before the dry period began, which would make it significantly older than conventional Egyptology accepts. Schoch's geological analysis has not been refuted. It has been ignored, disputed on non-geological grounds, and kept at the margins of mainstream Egyptology for 3 decades. Not because the geology is wrong, but because the implications are inconvenient for a timeline that is deeply established in the academic literature and the public imagination. Graham Hancock's synthesis of global evidence for a pre-Younger Dryas civilization, published in popular form but drawing on legitimate archaeological and geological data, has moved from being universally dismissed in academic circles to being the subject of serious, if sometimes hostile, engagement from mainstream researchers. Netflix's decision to produce a documentary series based on his work brought the hypothesis to a mass audience and generated a response from professional archaeology that was, notably, more engaged than dismissive. The conversation has changed. What the timeline revision actually requires is modest in its specific claims and profound in its implications. It requires acknowledging that sophisticated human technical capability, the ability to work stone at precision tolerances using processes we do not currently understand, to transport massive objects across challenging terrain without technologies we can identify, to build structures that withstand geological time while colonial-era construction beside them crumbles, existed earlier in human history than the standard model places it. Not aliens, not mythology. Human beings, thinking and working and building, in a period of human history that our current framework of knowledge has not yet adequately illuminated. Every decade, the oldest known example of complex human construction is revised backward in time. Each revision is preceded by the same institutional resistance, the same invocation of the established timeline, and the same eventual accommodation of evidence that the timeline could not absorb. Göbekli Tepe was impossible until it was excavated. The pre-Columbian Pacific contact was impossible until genetics confirmed it. The next revision is already being written in the microcrystalline surface features of stones that have been waiting, patient and precise, for someone willing to read what they say. The question that follows inevitably from everything the evidence presents is not just philosophical, it is practical. If the builders of the Peruvian megalithic walls possessed a knowledge of stone, working that modern science cannot replicate, and if fragments of that knowledge survived the colonial destruction in the practices, ceremonies, and oral traditions of indigenous Andean communities, then the recovery of that knowledge is not an impossible dream. It is a research program, specific, testable, and achievable with the tools and resources that currently exist. The geopolymer hypothesis requires a relatively simple test: comprehensive chemical and mineralogical analysis of joint zone samples from multiple Sacsayhuaman and Olan Taitambo stones, compared with laboratory-produced geopolymer analogues of andesite prepared using alkaline activators derived from locally available mineral sources. The comparison would either show the signature of geopolymer chemistry in the original stones, or exclude it. If it shows it, the mechanism is identified and can be developed. If it excludes it, the geopolymer hypothesis is eliminated and the investigation can focus elsewhere. The study requires sample access, laboratory equipment, and competent analytical chemists. Resources that are available and modest in cost relative to the significance of the question. The botanical hypothesis requires an ethnobotanical survey of Andean and Amazonian plant species, specifically targeting compounds with surface-level chemical reactivity toward aluminosilicate minerals. This is a more complex undertaking, but a tractable one. The methodology exists, the plant communities exist, and the analytical chemistry to evaluate candidate compounds against andesite samples is straightforward. The survey has never been conducted. A small, well-designed study, a single field season of botanical collection paired with a laboratory screening program could generate the first systematic data on this question in the history of the investigation. The acoustic hypothesis requires field measurement at the construction sites themselves. Precise mapping of resonant frequencies within the surviving wall structures, comparison of these with the acoustic properties documented at other Andean ceremonial sites, and experimental investigation of whether specific frequency ranges produce measurable surface effects in andesite samples under laboratory conditions. Acoustic measurement technology is accessible, non-invasive, and deployable in heritage site conditions without risk to the structures. Quipu decipherment, if it continues to advance at the pace set by Gary Urton's group and by the computational linguists who have recently joined the effort, could within a decade produce readable texts from the hundreds of quipus currently held in museum collections. If any of those texts contain technical construction information, if any a motor thought to record the process in knots before the extirpation, campaigns made that dangerous. The information is sitting in a museum drawer right now, waiting for a reading system to be completed. None of these research programs require extraordinary resources. What they require is the decision, by someone with the authority and funding to make it, that the question is worth asking formally. The mystery of the walls has persisted not because the evidence is too thin to investigate, but because no institution has yet committed to investigating it with the seriousness and resources it deserves. That situation is not permanent. The tools are ready, the questions are defined, the stones are waiting. There is a form of knowledge that no laboratory can generate and no analytical instrument can detect. The knowledge that lives in a community, transmitted across generations through relationship and practice, preserved in forms that protect it from external extraction, precisely because they are not legible to outsiders. For the specific knowledge of ancient Andean construction technique, if any portion of it survived the colonial period, this is the form it most likely took. Working with contemporary Andean indigenous communities as research partners rather than informants is not just a matter of ethical obligation, though it is that too. It is a matter of practical research design. The track record of collaborative research, where academic researchers approach indigenous communities as holders of legitimate knowledge rather than repositories of data to be extracted, is demonstrably more productive than the extractive model that characterized most of 20th century ethnography. In Bolivia, collaborative research with Aymara communities near the Tiwanaku site has produced insights into the construction sequences and material choices visible at the site that academic archaeology, working from the outside, had missed or misinterpreted. Community members, drawing on oral traditions that describe the site in terms of preparation sequences and material relationships, directed researchers' attention to features of the construction that turned out to be archaeologically significant. Subsurface foundations, material sourcing patterns, spatial relationships between structures that the conventional survey had not prioritized. The Quero communities of the High Andes, widely considered among the indigenous groups most continuous with pre-colonial Andean cultural practice, maintain ceremonial traditions that describe interactions with stone in language that is simultaneously spiritual and oddly procedural. An elder in a Quero community near Cusco described to a researcher a process of preparation of the ground, of the builders themselves, and of the stone that preceded any significant construction. The description used ceremonial language, but the structure of the described process, preparation, treatment, timing, testing, mapped onto the structure of a technical procedure rather than a purely ritual one. The elder was not trying to describe a chemical process, but something that was once understood as a chemical process may have survived in the form of a ceremony that preserves its structure without its explanation. These conversations are possible. They require time, trust, linguistic fluency, and genuine respect for the intellectual authority of the knowledge holders. They cannot be conducted as extraction operations, with researchers arriving with preformed hypotheses to confirm and leaving with what they came for. They require the kind of long-term relational investment that produces genuine exchange rather than one-directional information transfer. The knowledge, if it survives, is not sitting in a drawer waiting to be found. It is living in people, in the practices and ceremonies and stories of communities that have been navigating the gap between their preserved understanding and the world that colonization built around them for 5 centuries. Approaching those communities as partners in an investigation of shared human heritage, rather than as sources for an academic extraction operation, is not just the ethical path. It is the path most likely to find what the investigation is looking for. The history of technology is not a straight line from ignorance to understanding. It is a series of reconnections, moments when human ingenuity, facing a problem that conventional approaches cannot solve, reaches backward into the accumulated intelligence of the past and finds something useful that had been overlooked or forgotten. Roman concrete is the most discussed example in contemporary materials science. The concrete that Roman engineers used to build harbour structures in the 1st century BCE has survived 2,000 years of seawater immersion, barely any degradation. Modern Portland cement concrete, the material used in virtually every construction project on Earth today, begins deteriorating within decades in marine environments. The reason for the Romans' superior performance was not discovered until 2017. When a team of materials scientists analysed Roman harbour concrete and found that it contained a rare aluminum-rich mineral called tobermarite that forms as a reaction product between the concrete's volcanic ash component and seawater, actually strengthening the material over time rather than degrading it. For 2,000 years, the recipe was visible to anyone who could analyse a Roman harbour structure. For 2,000 years, modern concrete manufacturers produced inferior material because the conventional approach, Portland cement, aggregate, water, seemed like the obvious answer, and no one looked carefully at why the ancient approach worked better. When they did look, the answer was there in the material. encoded in the crystal structure of a mineral that had been growing quietly for millennia. The Peruvian walls could hold a similar gift. If the builders possessed knowledge of geopolymer chemistry, alkaline activation of aluminosilicate minerals, or surface treatment processes that altered the mechanical properties of stone at interfaces, then recovering that knowledge is not merely a matter of historical curiosity. Construction technology that could replicate the durability and seismic performance of the Sacsayhuaman walls, which have survived multiple major earthquakes that destroyed the Spanish colonial buildings built directly beside them, would be of substantial practical value in a world where infrastructure failure under seismic loading kills people and costs economies billions of dollars every year. The Amazon basin, whose plant chemistry may hold the key to the botanical hypothesis, is under severe deforestation pressure. Species are being lost faster than they can be catalogued, let alone chemically analysed. If there is a plant in the Amazon that produces compounds with stone-working properties, and the evidence suggests the question deserves investigation before it becomes unanswerable, the window for that investigation is not permanent. The stones of Sacsayhuaman are older than almost any human institution that currently exists. They have survived conquest, abandonment, earthquake, and the slow attrition of time. They have survived everything except our attention. The mystery they contain is not separate from the challenges of the present. It is a resource, a potential body of knowledge with real applications in a world that desperately needs more durable, more sustainable, more intelligent ways of building. The question is whether we choose to look or whether we wait until the choice is made for us by time. There is a particular kind of confidence that comes with the possession of a well-organized narrative. When the pieces of a story fit together, when the timeline is continuous, the sequence is logical, and the available evidence arranges itself into a coherent picture, the mind settles into that narrative with a satisfaction that can be difficult to distinguish from certainty. The mainstream account of ancient human civilization offers exactly this kind of narrative, a progression from simple to complex, from stone tools to agriculture to cities to writing to science, with each step following from the previous one in a sequence that feels inevitable. The problem with narratives is that they are not passive containers for evidence. They actively shape what evidence is gathered, what evidence is considered significant, and what evidence is set aside as anomalous. The philosopher Thomas Kuhn, in his 1962 study of how scientific revolutions occur, described this process with painful clarity. Normal science proceeds by solving puzzles within the framework of an established paradigm, and the puzzles it chooses to work on are selected, in part, by their fit with the paradigm. Evidence that does not fit, anomalies, are either explained away, set aside as puzzles for the future, or simply not pursued. The megalithic construction mystery is a textbook Kuhnian anomaly. It does not fit the established narrative of ancient human technical capability. It has been accumulating in the literature for decades, in geologists' field notes, in engineers' experimental results, in archaeologists' careful descriptions of joint surfaces that don't match what the conventional explanation predicts. It has been set aside repeatedly, not because the evidence is weak, but because the narrative that would have to be revised to accommodate it is deeply established and institutionally defended. Kuhn's insight was that paradigm shifts do not happen through the gradual accumulation of anomalous evidence alone. They happen when the anomalies reach a critical mass, when there are enough of them, and they are collectively important enough, that the energy required to explain them away exceeds the energy required to revise the paradigm. The question for the megalithic construction mystery is whether that critical mass has been reached, or whether it remains in the accumulation phase. The answer depends partly on sociology, on how the evidence is disseminated, who encounters it, and what the incentive structure of the relevant disciplines does to those who take it seriously. The rise of independent research publishing, documentary filmmaking, and public intellectual platforms outside the formal academic system has changed the dynamics of that sociologies significantly in the last 2 decades. Evidence that would once have remained confined to specialist conference proceedings can now reach millions of viewers. The audience for this investigation is not just academic, it is global and it is growing. The history of paradigm shifts offers a consistent pattern. Institutions resist, individuals persist, and evidence eventually prevails. Not always quickly, not always cleanly. But the arc of scientific history bends, slowly and unmistakably, toward the anomaly that refuses to resolve itself. The stones of Sacsayhuaman are one of those anomalies. They have been refusing to resolve for a long time. The question of what the ancient past looked like is not a neutral one. It is a question shaped by who is asking it, who is funding the investigation, whose evidence is credited, and whose testimony is treated as data versus decoration. For most of the history of professional archaeology as a Western academic discipline, those questions had answers that were depressingly consistent. European and North American scholars asking, Western institutions funding, empirical evidence from excavation credited, and indigenous oral traditions treated as colourful context rather than serious knowledge. The consequences of this structure are visible in the specific shape of what we know and what we don't know about the ancient Andean world. The sites that received thorough, well-funded excavation and analysis were those that offered the most legible evidence within the conventional framework. The Inca administrative centres, the well-stratified middens and building sequences that could be dated and catalogued within the existing timeline. The questions that didn't fit, the anomalous joint surfaces, the impossible precision, the construction methods that resisted conventional explanation, were acknowledged in field notes and set aside in print. The assumption of primitivity, the institutional expectation that non-European civilizations in the pre-colonial Americas were technologically simpler than contemporary European civilizations, was not an explicit policy of most researchers. It was a default baked into the training, the models, and the funding criteria of the discipline. Researchers who approached the evidence without that default, who asked, what does this evidence require, rather than, how does this evidence fit, found themselves working against the grain of their institutional environment. This matters practically, not just philosophically, for the investigation of the stone-softening mystery. The most significant archaeological evidence is not uniformly accessible. Sample collection from protected sites requires permits that archaeological bureaucracies grant preferentially to researchers working within established frameworks and pursuing questions that the existing paradigm validates. An independent researcher with a genuine question about geopolymer chemistry at the joint surfaces of Sacsayhuaman faces far higher barriers to sample access than an institutional researcher pursuing questions the conventional model finds comfortable. The decolonization of archaeology, the movement toward research frameworks that treat indigenous knowledge as legitimate, that involve community members as research partners, and that approach the past of non-Western civilizations with the same investment in complexity and capability that Western archaeological sites receive, is an ongoing process rather than a completed one. But it is creating openings that did not exist a generation ago. Indigenous researchers trained in Western analytical methods, who also hold cultural knowledge of their own communities, are beginning to ask questions that neither category of knowledge alone could formulate, and to investigate them with tools that neither tradition alone possessed. The mystery of the walls is, among other things, a test of whether archaeology can ask questions about ancient, non-European technical capability, without the constraint of the assumption, sure, that the answers must be modest. The evidence of Sacsayhuaman has been patiently providing the same answer for decades. Whether the discipline is ready to hear it depends on whether the institutional structures that shape the discipline have changed enough to let the evidence speak without the filter of a predetermined narrative. There is something quietly extraordinary about the fact that the mystery exists at all, not the mystery of who built the walls or how, though that mystery is real and profound. The extraordinary thing is that human beings, at some point in the past, did something that human beings today, with all of our accumulated knowledge and technology, cannot fully replicate. Not approximately, not cheaply, not yet. The walls of Sacsayhuaman define a boundary of human capability that we have approached but not crossed, despite 5 centuries of growing technical sophistication. This is not a familiar position for modern civilization to find itself in. The standard narrative of progress runs in one direction. from less capable to more capable, from simpler to more complex, from limited to expanded. The idea that we might be less capable than a past civilization in some specific technical domain is not just intellectually uncomfortable, it is structurally foreign to the way most people in contemporary society think about the relationship between the present and the past. But it is what the evidence suggests. And taking it seriously, sitting with the discomfort of it, rather than explaining it away, opens onto something important about the nature of human potential. If our species once possessed knowledge that we do not currently possess, then the limits of what we consider possible are not the limits of what is possible. The boundaries of human capability are wider than the present moment defines them to be. That is not a mystical claim. It is a logical inference from a factual observation. It also carries a warning. The immortals are gone, the quippus are burned. The oral traditions that survived are fragments. The distance between what the builders of Sacsayhuamman knew and what we currently know about what they knew represents a genuine, measurable loss, not of objects but of understanding, not of material but of capability. That kind of loss is not prevented by the accumulation of data. It is prevented by the maintenance of living knowledge systems, by the preservation of practices and relationships and forms of understanding that cannot be reduced to text files or database entries. The civilization that built the walls was not immune to catastrophe. Whatever knowledge they held, however extraordinary their specific capabilities in stoneworking, they and their knowledge could be destroyed. By conquest, by catastrophe, by the systematic targeting of knowledge keepers, by powers that understood what knowledge represents. The same vulnerability applies to every knowledge system that exists today, in every tradition and every discipline. The story of what happened to the knowledge behind the walls of Sacsayhuamman is not a story about the ancient past. It is a story about what is always at stake when knowledge lives only in the minds and practices of specific people, in specific places, in specific relationships that can be severed. The walls remember. We are still learning how to ask them. Stand back from everything this investigation has uncovered, and what you see is not a pile of disconnected anomalies. What you see is a coherent body of evidence, pointing consistently toward a single conclusion, that the construction of the pre-Inca megalithic walls of Peru involved knowledge and processes that we do not currently possess and have not yet adequately investigated. The replication failures are real. Skilled engineers and experimental archaeologists, applying the best understanding of conventional ancient construction methods, consistently fail to reproduce the specific combination of features that defines the original walls. Most critically, the three-dimensional, interlocking at the joint interfaces. This is not a marginal failure, it is a systematic one. The microscopic evidence is real. The flow features, compression indicators, and localized vitrification documented at joint surfaces are physical facts embedded in the material. They require an explanation, and no current explanation adequately accounts for them. The cross-cultural legends of stone softening agents are real, documented by credible chroniclers across multiple independent traditions, describing a consistent phenomenon in terms that map onto plausible chemical mechanisms. They represent a pattern that deserves investigation rather than dismissal. The destruction of Andean knowledge systems was real and deliberate. The extirpation campaigns removed, with institutional thoroughness, the living knowledge structures that most likely held the technical understanding behind the construction methods. The absence of an explanation in the surviving literature is not evidence that no explanation existed. It is evidence of how completely the explanation was targeted. The global pattern is real. The same specific combination of anomalous features appears at megalithic construction sites distributed across the planet, in cultures too distant and too separated in time, to be explained away as regional variations on a single known tradition. And the scientific investigation of all of these threads remains, by any measure, inadequate to the scale and significance of the question. The geopolymer analysis has not been done. The botanical survey has not been conducted. The acoustic mapping of construction sites has not been systematically undertaken. The Quipu corpus has not been deciphered. The collaborative research programs with indigenous knowledge communities have not been adequately funded. The walls of Sacsayhuaman have survived earthquakes that collapsed Spanish colonial buildings constructed directly beside them. They have stood while the civilization that built upon them rose and fell, while empires arrived and departed, while the world that surrounded them transformed beyond recognition. They are still standing. The question is whether we are ready to approach them with the full seriousness that the evidence they contain deserves. Come back to the beginning. Back to the high cold air of Cusco, the thin light of the Altiplano, the wall that rises from the earth in its great irregular curves. Everything looks the same as it did when this story began. The stones have not moved. The joints are still impossibly tight. The light still moves across those ancient faces in the morning, with a quality of revelation, as though the stone itself is turning toward something just out of frame. But you are different now. You are standing before the same wall with a different body of understanding, and that understanding changes what you see. You see a construction achievement that exceeds, in specific measurable ways, what modern engineering can replicate. You see a surface that carries microscopic evidence of a process no one has fully explained. You see the product of a knowledge system that was deliberately targeted and systematically destroyed, and whose fragments survive in the hands and voices of communities whose relationship with these stones predates the oldest institution in the world. Today, you see a question that has been waiting, embedded in stone, for the right combination of tools and will and intellectual honesty to answer it. Not an alien mystery, not a conspiracy. A genuine scientific frontier, the kind that feels, from inside the established consensus, like transgression, and feels, from outside it, like the next obvious step. The people who built these walls were not incomprehensible. They were human beings, curious, capable, working within a knowledge tradition that gave them access to capabilities we have since lost. They were not trying to baffle us. They were trying to build something that would last. And they succeeded, beyond any reasonable definition of the word. The walls have lasted. The knowledge has not, or not entirely, not visibly. But the walls themselves are a form of knowledge, if we are willing to read them. That reading requires geologists willing to look at surface evidence without the constraint of what their paradigm says the surface should show. It requires chemists willing to ask whether the Amazon holds compounds that existing surveys have overlooked. It requires archaeoacousticians willing to map frequencies at construction sites with the question of stone working explicitly in mind. It requires ethnoarchaeologists willing to sit with indigenous knowledge holders long enough and listen carefully enough for the ceremony to reveal the procedure it encodes. It requires, most fundamentally, the willingness to let the question be as large as the evidence makes it. Not larger, not into territory the evidence doesn't support, but as large as it actually is, which is large enough to matter, large enough to revise something important about what we believe we know, large enough to have been waiting, in stone, for someone to take it seriously for 500 years. There is one stone in particular, no name, no special designation, no marker distinguishing it from the hundreds of others around it, that sits in the lower course of the northeastern section of the Sacsayhuaman walls. It is not the largest stone in the complex. It does not display any obviously remarkable features. It is simply one stone among many, fitted against its neighbours with the same impossible precision that characterises every joint in the wall. This does here before Peru was called Peru. It was here before the Inca came, before the Spanish came, before the English word stone existed to describe it. It was shaped and placed and pressed into contact with its neighbours by hands that held a knowledge we have not yet recovered during a period of human history that we understand only in outline. It has survived everything that time has sent against it. Seismic events that registered on geological records across the continent, colonial hammers that took other stones from the upper courses of the wall for Spanish cathedral foundations, the slow chemical conversation between rock and rain that dissolves most stone formations over centuries. It has not moved. It has not cracked along the joint line. It has not yielded. The people who placed it did not know they were creating a mystery. They were simply doing the work, applying a knowledge that was, to them, ordinary. The way a skilled carpenter applies joinery techniques that feel natural after years of practice, without stopping to theorize about the physics of wood grain. The mystery is ours, created by the distance between what they knew and what we remember of what they knew. But mysteries are not permanent conditions. They are temporary, states of insufficient knowledge waiting for investigation to resolve them. The investigation of the Sacsayhuaman walls is not over. It is, in the most meaningful sense, barely begun. The tools that exist today to read the evidence in the stone are more powerful than any that existed when the question first began to be formally asked. The collaborative frameworks that can bring indigenous knowledge into genuine partnership with scientific analysis are more developed than they have ever been. The global community of curious, rigorous, intellectually honest people who refuse to accept incomplete explanations for extraordinary physical evidence is larger than it has been at any point in history. The stone is still here. The question is still open. And somewhere in the gap between what the stone knows and what we have been willing to ask, in the joint surfaces, in the Amazon's unknown chemistry, in the knotted cords of undeciphered quippus, in the ceremonies of communities who remember without knowing what they remember, the answer is waiting. It has been patient. It will wait a little longer, but not perhaps for much longer.